Welcome, ladies and gentlemen, to a lecture on using conservation of momentum to solve some physics problems. Today I'm just going to solve two example problems just to model a couple more problems where we use conservation of momentum to solve for some quantity that we want to find. Okay? So let's look at the first problem. Consider firing a 30-06 rifle. If you're shooting an approximately 12-gram 30-06 bullet out of a rifle with a 61-centimeter barrel, the bullet will leave the gun with a speed of 820 meters per second. The gun has a mass of 3.7 kilograms. If the gun wasn't held in place by anything, what speed would it have when the bullet left the gun? If you have a mass of 100 kilograms and you hold the gun right up against your shoulder so that you and the gun move together, what speed will you have as the bullet leaves the gun? Okay, so we have our gun here. Looks kind of like this. And we have a bullet that leaves it. Alright, so the mass of the gun is mg. The mass of the bullet is mb. The bullet has some velocity, vb. And then we want to find vg, okay? And vg is this velocity that the gun has when it goes backward, okay? Now, if you ever learn how to shoot a real gun, when you shoot a rifle, what they tell you to do is make sure that this back end of the gun is real tight up against your shoulder, okay? You pull it up into your shoulder and you pull it in real tight so that when the bullet leaves the gun, the mass on the other end of our conservation of momentum is you plus the gun, because that's a great big mass, right? If it's just the mass of the gun, then the gun goes flying back. Like if you left a little gap between the gun and your shoulder, then the gun goes flying back and basically punches you in the shoulder, okay? It's pretty uncomfortable. So what we're going to do is we're going to solve for the speed that the gun would go flying back with if you don't brace against it, and compare it to the speed when you pull it right up tight against your shoulder and then shoot the gun, okay? Okay, so we're going to use conservation of momentum to solve this. So Pi equals Pf. And this isn't a collision, right? So we're not talking about elastic versus inelastic. You know that non-conservative work is being done. There's chemical energy in the gunpowder, right? And what happens when the gun shoots is we light the gunpowder on fire. We get all of the chemical energy out of the gunpowder, and it propels the bullet forward and the gun backward, okay? And the rate that it propels each forward and backward is dependent upon this conservation of momentum, okay? So, initially, bullets sitting in the gun, we haven't pulled the trigger yet. We have Pi equals 0, right? You're both just sitting still. So the velocity of the gun is 0 initially. The velocity of the bullet is 0 initially, so the momentum of each is also 0 initially. Final, you can see if we have this coordinate system that I've drawn where x hat goes to the right, we'll have the mass of the bullet times the velocity of the bullet. That's the momentum of the bullet going forward. And then the momentum of the gun, mg minus vg, okay? So it's the mass of the gun times the speed of the gun, and then the minus is what turns my speed into a velocity, right? It's in the minus direction, okay? So then the speed that the gun goes backward with is really easy. The speed is mb over mg times vb, okay? So it's the speed of the bullet times this ratio of their masses, okay? And if we put in the numbers for this, I believe we get that Vg equals 2.7 meters per second, which is approximately 6 miles per hour, which is like a slow jogging speed. So it's like if a person was jogging along slowly and ran right into your shoulder. But it's on a little tiny object that hits you in the shoulder very abruptly. So pretty uncomfortable, okay? So if you have a little gap between the back of the gun and your shoulder, you get popped by this thing at 6 miles an hour, it's not very comfortable. Does it break bones in your shoulder or anything like that? No, right? It's not going that fast, but it bumps into your shoulder. It's not very comfortable. So now let's look at the problem where we have the gun pressed right up against our shoulder, and you can see up here on the right, I've said big M is our mass, okay? And let's say, just for the sake of round numbers, we have a mass of 100 kilograms. So now the gun's right up against the shoulder, we have a mass of 100 kilograms. Before, it doesn't change anything, right? You and the gun are sitting still, bullet's sitting still, so initial momentum is 0. That's equal to, now final momentum, we still have MB VB, right? The bullet goes out, the gun goes forward. Minus, now this object is a conglomerate object, just like when two objects stick together and we have the conglomerate object. Now, with you holding the gun up against your shoulder, you're turning you and the gun into this conglomerate object where you have M plus mg, okay? Big M, our mass, plus the mass of the gun. And then that's this new VG. VG in this case is equal to MB. Now over the sum, M plus mg times VB, okay? And you can see what we did here is we just made in this ratio of masses, we just made the denominator way bigger, right? And so what does that do? It makes VG way smaller, right? And that gives us a VG that's equal to, I believe if we plug in the numbers here, we get 0.095 meters per second, which is about 0.2 miles per hour, okay? So that's nice. That's a lot slower, right? Now we have just a little bit of motion coming out of this, okay? Just a little speed that us leaning forward is gonna dissipate off real quickly, okay? Now let's consider something a little more interesting from this, okay? We see people get shot in movies all the time, right? Good guy shoots the bad guy in a movie all the time. American movies are nothing if not violent, right? We see all the time in movies where the good guy shoots the bad guy and the bad guy is like launched backwards through a wall or something like that, right? You see a guy like, good guy runs in, kicks down the door, pulls a shotgun, shoots the bad guy goes flying backwards, right? Could that really happen? Is that the way that really works? Let's look at it through conservation of momentum, okay? When the good guy shoots the gun, we have the same thing that we just solved for, right? And so we end up with VG equals MB over M plus mg times the velocity of the bullet, right? Then when the bullet goes and hits the bad guy, we're going to have conservation of momentum again, right? This time we're going to have an inelastic collision between the bullet and the bad guy, right? The bullet presumably is going to deform the bad guy. That's kind of the point. And they're going to collide, right? So when the bullet hits the bad guy, our initial momentum is the mass of the bullet times the velocity of the bullet, right? And then the bad guy is just kind of standing there, okay? So we'll say his velocity is 0. And then afterward, we have some new conglomerate object, okay? And let's say the mass of the bad guy is the same as the good guy. So we'll just use capital M again for his mass. And now this conglomerate object is the mass of the bad guy plus the mass of the bullet, right? The bullet and the bad guy are one object now. And then they have some V final, right? The bad guy's V final after he gets hit by the bullet. So what's this V final? V final is equal to the mass of the bullet divided by the mass of the bad guy plus the mass of the bullet times the velocity of the bullet. Now remember this VG, we called it the velocity of the gun before, but now the G can be good guy, okay? So the velocity of the good guy is the mass of the bullet divided by the mass of the good guy plus the mass of the gun times the velocity, right? Now the mass of the bad guy, or the velocity of the bad guy after this collision, is the mass of the bullet divided by the mass of the bad guy plus the mass of the bullet, right? Times the velocity of the bullet. So you can see, first off, mass of the bullet versus mass of the gun. There are no guns that shoot bullets that have a greater mass than the gun, right? Because if that was the case, what you would get is the gun flying backward with all the speed while the bullet flies forward with the little speed, right? You can't shoot a bullet that has a mass way bigger than your gun, because you're going to send your gun flying backwards. You're going to send your bullet flying forwards not very fast, okay? So that doesn't work. So really, this velocity final of the bad guy, it's going to be slightly bigger than the velocity of the good guy, because this thing, the denominator, is smaller, right? But not by a lot, right? The mass of the good guy plus the gun is still basically the mass of the good guy, right? When we used the example, we said the good guy weighs 100 kilograms, the gun weighs 3.5 kilograms. It's basically just the mass of the good guy, right? The mass of the bad guy plus the mass of the bullet, well, now we're really talking about that's just the mass of the bad guy, right? So really, both of these look like VF is approximately equal to VG is approximately MB, or let's say, instead of approximately, we'll say it goes like the mass of the bullet divided by the mass of the person, VB. Okay? So these two speeds, the velocities would be in different directions, right? This one we said was in minus x. This one, if this goes over and hits the bad guy over here, this is going to be VF, right? So VF is going to be plus x. So they're in different directions, but the speeds, you can see, would have to be the same. So what does that tell me? In my movie, if the good guy shoots the bad guy and the bullet hits the bad guy and he goes flying back through the wall, this whole line of thinking tells me that what should have happened when the good guy shot the gun is he should have gone flying back the other way, back through the other wall. And the bullet should have knocked the bad guy through one wall, and the kick of the gun should have knocked the good guy back through the other wall. Okay? That's the only way that that actually works within conservation of momentum. All right? So when we see this in movies, we know it looks a little off, but the truth is it's utterly ridiculous, right? If we look at it through conservation of momentum, this is an absolutely absurd thing to happen in movies. And indeed, this was more common, I think, in older movies, and as people started to chuckle about the absurdity of it, I think it's a little less common. It still happens sometimes in modern movies, but a little less common in modern movies unless you do it for a comedic effect, okay? Okay. So now let's look at one last example. And this is the example that I think I said when I first introduced conservation of momentum, when I first introduced elastic collisions. I think I said that I would do this example at some point in the future, okay? So let's go ahead, let's get to it now. In this example, we're going to take my wife and we're going to grab two of these big Swiss exercise balls that you might have seen at the gym, okay? They're nice and bouncy, and what those are going to do is we're both going to hold them in front of us, and using these big bouncy balls is going to allow us to have a collision that we can approximate as an elastic collision. Okay? So we're going to run at each other and we're going to have an elastic collision holding these two balls. Now, let's say we're both going to run flat out as fast as we can. So let's draw a picture. Here's my wife. She has this great big ball in front of her. She's going to run this way. We're going to call that V2, and she has mass M2. And here's me. I have the big ball over here. I'm running this way. I'm going to have mass V1, velocity V1 and mass M1. Okay? And we run at each other. We'll use X hat to the right. And then let's get some realistic values for these things. So my mass is like 140 kilograms, I think. It's pretty high. My wife's mass, she's much, much smaller than I am. Her mass is more like 60, I think 61 kilograms, something like that. Okay? Now, for my velocity, if we're running flat out, let's say my V is 8 meters per second. I probably used to be faster than that. I'm probably slower than that now. Whatever. We're going to say 8 meters per second. For her velocity, she was generally not quite as fast as me. We'll say 6.3 meters per second. Okay? So we kind of put some numbers on that. And then let's ask, what's my final velocity? And what's her final velocity? And go ahead and pause the video and think about this and guess. Okay? Okay. So, right out the bat, we can make a little guess here. So we know we're going to have an elastic collision. And if we look at the masses of the two objects here, myself and my wife, we don't quite have the freight train and the baseball thing going on here, but we're getting close, right? We definitely have kind of the human version of the freight train and the baseball going here. I'm more than twice her size. So probably what we expect is her velocity to be pretty big and going in the opposite direction after we bang into each other, right? And we expect my velocity to go down during the collision, but probably not change directions, right? So let's solve and see what happens. We're going to solve it with conservation of momentum, which tells us that Pi equals Pf. We have a one-dimensional problem here, which is going to be really convenient. And then we have an elastic collision, which tells us that Ki equals Kf, right? That's what the Swiss ball is for, is to make it an elastic collision. And if you haven't noticed yet, elastic collisions result in much greater impulses, because when we don't dissipate the kinetic energy in sticking the objects together, the change in velocity for at least one, if not both of the objects, is much bigger, okay? They tend to bounce back in like the opposite direction that they came in, kind of thing. So our changes in velocities tend to be much bigger. So this is much worse for her than if we both just ran at each other and just slammed into each other without the Swiss balls, right? Because then we would have an inelastic collision. In this case, we have an elastic collision, so her change in velocity is going to be much bigger in this than if we just ran into each other without the exercise balls here, okay? So let's look at the conservation of momentum first. She has m2 v2. That's her momentum, right? My momentum is going in the negative direction, and it's m1 v1, okay? Afterward, we have m2 v2 final, and then plus m1 v1 final. And we're just going to write it as plus and let the signs come out as they will, okay? We're being non-committal about what direction each person is going after the collision. And then we can write the energy too, right? 1/2 m2 v2 squared plus 1/2 m1 v1 squared equals 1/2 m2 v2f squared plus 1/2 m2 m1 v1f squared. Okay? And then much like I did when I did the billiard ball one, the billiard ball one was essentially this problem, but one of the objects had an initial velocity of 0, right? Now both objects have this initial velocity, but it's otherwise it's a very similar problem, right? Only now when we go to see what's going to happen at the end, the masses are dramatically different instead of the same, okay? So I'm going to do the same trick where I bring the m1s all to one side, and that gives me, from the momentum equation, m1 equals v1f plus v1, or m1, not equals, m1 times v1f plus v1 equals m2 times v2 minus v2f. Okay? And then I'm going to do the same thing with the kinetic energy equation. I'm going to bring all the M2s to one side and all the M1s to one side, and I'm going to end up with M1 V1F squared minus V1 squared equals M2 V2 squared minus V2F squared. Okay? And notice this one, right, is delta V for me, and this one is minus delta V for my wife. And so this equation, if I look at it, what it's telling me is if I added the 1/2 back in, what it would tell me is that delta K for me is equal to minus delta K for my wife. Okay? So whatever because kinetic energy is conserved in an elastic collision, whatever kinetic energy I lose, she gains. Okay? So the question about this is really how much of my kinetic energy do I transfer to her? Okay, so then this equation, I can do the same trick that I did again with the billiard balls. These differences can be written as a sum times a difference, right? So I can have V1F plus V1 times V1F minus V1, right? And that's the same as this left side. And then I have M2, and I do the same thing. V2 plus V2F times V2 minus V2F. And then I can do the same trick where I divide one equation. I divide the this equation by the momentum equation, right? And you can see that this V1F plus V1, that's going to cancel. The M1 is going to cancel on the left side. And I'm going to have, let's make a little space. So I take equation 2 down here. I divide it by equation 1. So I divide the left side of equation 2 by the left side of equation 1. I get a canceling of the M1, the V1F plus V1. And the term that's left is this V1F minus V1, right? And then I do the same thing to the right side. And I get a very similar kind of cancellation, but now I cancel the difference on that side, right? And what I end up with is V2 plus V2F. And then that tells me that V1F equals V2 plus V2F plus V1. Okay? And then if I stick that in to equation 1 here, then what I get is I have M1 times V2 plus V2F plus V1 and then plus V1, right? That was me substituting out the V1F equals M2 V2 minus V2F. So then I have V2F times M1 plus M2. Okay? That's equal to M2 V2 minus M, oops, not a V, an M, M1 V2 minus 2 M1 V1. Okay? And that tells me that V2F equals M2 V2 minus M1 V2 minus 2 M1 V1 over M1 plus M2. So this is my wife's final velocity after we have this ill-advised collision. Okay? Now, you can see if you look at this, that this is going to be negative. Okay, so she's running in the positive x hat direction to start, but we have m2 and v2, and that's the smaller mass and the smaller velocity. That's positive, but then we're going to subtract the bigger mass times the smaller velocity, and we're going to subtract 2 times the bigger mass times the bigger velocity. Okay, so this thing's going to be negative, not just a little negative. It's going to be dramatically negative. Okay, and if we plug in numbers, we get minus 13.62 meters per second, or to 2 sig figs, minus 14 meters per second. Okay, and that's around minus 31 miles per hour. Okay, that is a bummer. Okay, so this is why when I showed my wife this example, she immediately said, yeah, that'll never happen, right? Because that would be a real bummer. And indeed, we wouldn't want to do this. This is somebody getting blasted back in the other direction, probably hitting the ground, getting a concussion when their head hits the ground, that kind of stuff. This is a really bad idea, okay? So like I said, we're in not quite baseball and locomotive territory, but we're getting pretty close to freight train and baseball territory here. Her velocity changed dramatically from 6.3 meters per second in the positive direction to minus 14 meters per second. Okay, so 14 meters per second in the negative direction. So her total change in velocity is 20.3 meters per second. That's a really big change in velocity to have in the instant that it takes for this collision with the exercise balls. Okay, now for my velocity, we can just take this equation right here and just substitute out v2f, and we get v1f equals v2 plus v1 plus, and then v2f is all of this stuff down here. And then if we simplify by making the denominator of each term the same, right, multiplying by 1 so that the denominator of each term is the same, just like I did with the billiard ball problem, then we can simplify this to 2 m2 v2 minus m1 v1 plus m2 v1 over m1 plus m2. And if we do that, what we'll see is that this V1 final is about minus 0.68 meters per second, which is approximately minus 1.5 miles per hour. So then when we do that, with these changes in speeds, what we can see is we had this elastic collision, and kinetic energy was conserved and momentum was conserved, just because momentum is always conserved, right? And in conserving that momentum and conserving that kinetic energy, what happens is I transfer some of my kinetic energy to her. Quite a bit of it, actually, right? My speed is very low at the end, right? It says minus, but remember, I was going in the minus direction, right? So this thing was a minus 8 meters per second. And now it's under 1. So most of my speed is gone. I've transferred a lot of my kinetic energy, and I transferred it into my poor wife in this situation. And what happened was her kinetic energy increased dramatically, and her delta P was really big because her velocity actually changed directions, okay? Now, you can see this was a rather extreme example, right? Both of us running flat out at each other while I'm much, much bigger than she is. You can go find videos of people actually doing this on YouTube, and it has comically terrible results almost invariably, okay? Now, generally these people don't run flat out at each other as fast as they can, right? And thankfully not, because we can see there's a lot of energy in the problem if you're both running as fast as you can. And also, usually the two people doing it don't have a mass that's so dramatically different. They usually have a mass that's actually pretty close to equal, okay? And still, the results of doing this are, comically bad, okay? You can watch and see that somebody's velocity coming out of the collision is much, much higher and in the opposite direction, okay? So go watch those videos with an eye for the physics behind it, and laugh at these poor people's misery, but also pay attention to, you can see these principles in action when people do this, and these using these exercise balls to bump into each other allows people to have near elastic collisions, which have much more dramatic results than the normal collisions we see between people that are very, very inelastic, right? So that concludes our examples for conservation of momentum. We'll look at some more stuff in future lectures, and we're gonna move on to different topics in the next lecture. So the homework, there's still homework for this, and that'll be the end of our conservation of momentum homework. And by that point, you should have a really good conceptual idea of how conservation of momentum works.